now we are moving on to 1.5, measurement, uncertainty, accuracy, and precision. So in this section, we're going to talk about defining accuracy and precision, distinguish between exact and uncertain numbers, correctly represent uncertainty in quantities using significant figures, and apply rounding rules to computed quantities. Real quick though, your book does not go through scientific notation. It assumes that you have seen it before. So I'm going to go through what scientific notation is before we get into this chapter as a quick review. So scientific notation is a way to write numbers at really big or really small numbers a little easier and better. So there are two parts to scientific notation. You have the main number. You have your digit, which is greater than 1 but less than 10. So basically 1 to 9, greater than or equal to 1. Okay, and then you have your power of 10. So what we do with scientific notation is you have your digit and you multiply it by however many powers of 10 to get the number you're trying to represent. So for example, let's say we have a number of 298,000. Okay, to put this in scientific notation, the first thing we need to do is identify where our number between 1 and 10 is going to be. So we look at this, okay, 2.98 gives us is greater than 1, less than 10. So this is going to be 2.98 times 10 to some sort of power. So to figure out that power, this decimal place to get us back to 298,000 has to go 1, 2, 3, 4, 5 spaces. So this is 10 to the 5th power. So this is 2.98 times 10 to the 5th power. Okay, so these represent the exact same number. You can also do this for decimal places or numbers less than 1. Okay, so for instance, 0.000025. So the same thing, we find where we can make a number between 1 and 10. So we can put our decimal here, make this 2.5 times 10, and this needs to go 1, 2, 3, 4, 5, 6 spaces. Now because this is a decimal, it's less than 1, this is 10 to the negative 6th power. We move the opposite direction. Now if you're given a number in scientific notation and you want to put it back into its standard form, so let's say we have 5.3 times 10 to the 6th power. The way that I do it, I'm a very visual person. So I write 5.3, and then I take my decimal place and I go, okay, 1, 2, 3, 4, 5, 6. So there's my 6 spaces. So this is where the decimal place would be. And every little space that I made there gets a 0. Or if you have it to a negative power, same type of thing. Let's say we have 2.19 times 10 to the negative 4th power. I'm going to start by writing 2.19, and then this time though my decimal needs to go to the left. So we have 1, 2, 3, 4. Decimal place. So this is 0.000219. And this guy over here, 3, 0, 0. This is 0.000219. Notice the 0 in front of the decimal place. You really don't have to put that, but it's you know, it's implied because it's 0 point something. Appendix B in your book also talks a little bit more about this. If you need more practice or if you have questions, please ask me. So, when it comes to taking measurements, counting is the only type of measurement that is free from uncertainty. Okay, for instance, I have 3 cats because I could count them 1, 2, 3. It's exactly 3. This is called an exact number. You know, I don't have 2.5 cats, even though one of my cats is missing an eye, but no, she's still a cat. She's still a whole cat. Okay, so again, this is an exact number. You can think of this as having an infinite number of decimal places. So I have exactly 3.000000000 cats. Okay. The numbers for defined quantities are also exact. So 1 foot is exactly 12 inches. 1 inch is exactly 2.54 centimeters. These are defined numbers that are exact quantities. 1 gram is exactly 0.001 kilogram. Now, if you have some quantity that comes from a measurement that's not counting, so maybe you're looking at the length of something, there are some uncertainties. These are not exact numbers. So there's limitations to the measurement process. So you have to report a measured number to indicate what its uncertainty is. And there is, for instance, when recording a measurement, you get to estimate 1 uncertain digit. So for instance, we have what's called a graduated cylinder here. And let's say I wanted to measure what this volume is. So if we zoom in on it, the first thing that we should do is whenever we read the volume of something, notice it has this kind of curved surface. This is called the meniscus. And if we notice here, this water surface, it's between the marks for 21 and 22 milliliters. So I can't really call this 21 milliliters. I can't call it 22. This is the bottom of the meniscus. Okay, that's where we make a reading from. So I know it's 21 point something. Okay, so I can say with accuracy, with certainty, that it's greater than 21. But I don't know, okay, is this 21.5? Is this 21.6? 21.4? This is where your guess measurement comes into play. So for instance, it seems a little bit closer to 22 milliliters, so maybe we're gonna say it's 21.6 milliliters. Okay, but maybe some of you think, oh no, I think it's more like 21.5 milliliters. That's fine too. Some of you may say it's 21.7. Okay, all of us may have a different guess digit. But we can't go, okay, this is 21.60, right? Because we can't say that with certainty. Now, this type of concept is true for all measurements. A kind of good way to decide if you have a guess digit or where your guess digit should be is you look at how things are divided and then you go 1 space over. That's your guess. So this goes, okay, 20, 21, 22. So since this is going to the ones place, okay, or this graduated cylinder for the whole thing, that means that our first decimal place, so before the decimal is good, after the decimal, 1 digit for our guess number. So tenth of a milliliter here. So again, the 2 and the 1 from that reading, the 21, those are certain digits. We know it's more than 21. And the 6, remember 21.6, is an estimate. Again, maybe one of you would have said 21.5 or 21.7 milliliters. But one thing that all of these digits are called significant figures or significant digits. Usually significant figures is what we say, and one thing to know about chemists is we're lazy, so we've abbreviated this to sig figs, and it sounds cuter. So the significant figures in a number tells us how accurate and precise or how confident we are in a measurement. So to know if a number is a significant figure, okay, it is always going to be significant if it is not 0. Okay, so non-zero digits are automatically significant. A captive 0, that means you have a 0 in between two numbers. So, something like 309. This 0 is significant. And then trailing zeros, but these have some special parts, okay? Trailing zeros when they are to the right of the decimal place or when they are in scientific notation. So for instance, if I have, the number 3.0, okay? This decimal is the 0 is to the right of the decimal place, it is significant. So this number has two significant figures. Or if I'm in scientific notation, which you can use to show significant figures for a big or a small number. So for instance, I have 2.90 times 10 to the 5th power. Only the numbers in your main number part, these are the only place where significant figures come into play. The times 10 to the 5th, that's only zeros. Those zeros are considered placeholders. They are not significant. Okay, so this has 3 significant figures, the 2, the 9, and that 0. Because it's after the decimal point, it's in scientific notation, it is significant. Now, there are times when zeros are not significant. For instance, when they are leading. So if I have a number like 0.005, these are all leading zeros. There's no number in front of them, nothing. So these are just placeholders. They are not significant. Now, if this was 10.005, then they would be significant because they're sandwiched or they're captive zeros. So this 0.005 has 1 significant figure, and 10.005 has 5 significant figures. And then another one that are not significant are trailing zeros to the left of the decimal place. So these zeros can often be kind of hard to really say if they're significant or not. So for instance, the number, well, actually looking back at the 0.005, these are leading zeros. They're to the left of the decimal place. They are not significant. So we're going to look through some more examples. So here's a couple numbers that we can try to identify the number of significant figures. This first one on the left, 3090. Of course, the 3 and the 9 are significant, and the 0 that's sandwiched in between is significant. Then we have this trailing 0, but it's before decimal. There's no decimal place here, so we really can't say that this is a significant 0. But we can say with confidence this has 3 sig figs. Now this other number, 0.008020, we have these 3 leading zeros. So these are not significant figures. But the 8, the 2, sandwich 0, and then this trailing 0, because it's after a decimal point, these are all significant. So this has 4 significant figures. So there are measured numbers that we can then use these significant figures to figure out how many significant figures should be in our answer. So when it comes to adding and subtracting, what we do is you line up all your numbers by their decimal point. And so for instance, let's say we have 50.0, we have 102 without decimal points, and we have 5.78. Okay, so you can, and I'm just going to do them all as adding. So we can add down 107.78. But your final answer should have the same number of decimal places as the number with the least number of decimal places. So if we look at these original numbers, 50.0 has 1 decimal place, 102 has 0, and 5.78 has 2. So our final answer then should have 0 decimal places. So that means that we need to get rid of these decimals. So we need to do some rounding. So this isn't going to be 107 because this next digit away we're dropping from the 7 is higher than a 5. We need to round up. So this rounds to 108. Now multiplying or dividing numbers is a little different. So here the way it works is you're going to take the number with the least number of significant figures, and that is how many overall sig figs in your final answer. So let's say we have 5.0 times 1.32 times 0.00570. So we look at each of these numbers, and I see that 5.0 has 2 significant figures, 1.32 has 3, and 0.00570 has 3. So our final answer should be 2. So then we get out our handy dandy calculator and we type all these numbers in. And my calculator answer is 0.03762. Now only 2 significant figures, which means these last 2 numbers need to piece out. So we need to figure out how to round this number. So the first number I'm dropping, that 6, is greater than 5. So that means this is going to round to 0.038. So, and that's what point number 3 is. The digit to be dropped, and then immediately to the right digit we're keeping is less than 5. We round down, we keep the number as it is. Okay, if it's higher than 5, then we round up to the next digit by 1. If the drop digit is 5, this is a new rule that I've never seen, but if your number that you're dropping is 5, then you can either round up if that gives you an even value, so if like it's okay, or you round down or keep it as is to keep it an even number. So here's some examples to look at. 0.028675. We want to go to 3 sig figs. Okay, so that would be 286 here. The 7, since that's what's being dropped, tells us the 6 needs to round up. 18.3384. Okay, that's where we're dividing it. Our number is, or splitting it, our number is less than 5, so we're rounding down to 18.3. 6.8752 rounds up, and 92.85 rounds down. Okay, so I want to kind of talk about these last two. 6.8752 rounds up because our first digit that we're dropping is that 5, And since it's next to a 7 is our last digit, we're going to want the final number to be an even number. So it's going to round up to 6.88 to make it an even number. 92.85, okay, the 5 we're dropping, but we're already at an even number. So this is going to stay as 92.8. Okay, so this next problem here is we are going to use what is called water displacement to find the density of this mass of metal here. So density, if you remember, is equal to the mass of something divided by its volume. So something like a piece of metal, we can easily find its mass. Okay, and so it was weighed or found the mass to be 69.658 grams. So to find out the volume of something, that we can't just stick this in a measurement type environment, we need to do a different version, and we're going to use what is called displacement. So displacement is something that you guys have seen. For instance, if you take a bath, when you get into the bathtub, the water level goes up. But did the actual amount of water change? No. Okay, but it goes up because it's increasing by your volume. So that's what we are going to be using to find the volume of these metal pieces. So you start by taking a graduated cylinder, that's what these pieces of glassware are called, and we are going to pour some water in it and measure our initial volume. So they measure this initial volume to be 13.5 milliliters. And then we take our piece and we drop it in the water, and the water level is going to go up. And that difference in volume is equal to the volume of the object. So now it's gone up to this final volume that they read at 22.4. So our volume of our metal, of our mass, is equal to our final volume minus our initial volume. So this is equal to 22.4 minus 13.5 milliliters. And this is equal to 8.9 milliliters. So notice when I did this math, our final answer should only have one decimal place because both of these only have one decimal place. Boom. For our final answer for volume. And also notice now we only have two significant figures, which is fine. Okay, that happens. So now we have our volume. I guess it's not our final answer, it's our volume answer. So now to calculate our density, we're going to take our mass, which is 69.658 grams, and we're going to divide it by our volume, which we calculated to be 8.9 milliliters. Or cubic centimeters, whatever you want to call it. They're the same thing. And so we get now a density of 7 point and a bunch of decimals, right? Blah, 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 blah. Grams per milliliter. But how many sig figs should this final answer have? On top in our equation, this mass number has 5 significant figures, but our volume only has 2. So our final answer should only be 2 sig figs. So there's 1 at the 7 and then the 8, so that means everything after the 8 is dropped off. The number, that first dropped off number is 2, that is less than 5. That means our density is rounded down to 7.8 grams per milliliter, or grams per cubic centimeter. So this is density by displacement. here's another one. So we're given a mass and we're given our displacement volumes. So the volume of this is 19.8 minus 17.1. So we have a volume of 2.7. This time I'm just going to call it cubic centimeters because why not? They're the same thing. So now our density is equal to 51.842 grams divided by 2.7 cubic centimeters. Our final answer should have 2 sig figs because of our volume is only 2 sig figs. So this comes out to look like 19.2 blah 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 blah, but only 2 sig figs, which means that 2 goes bye-bye and this rounds to just be 19 grams per cubic centimeter. Now here's the cool thing about density. Remember, it's an extensive property. That means an intensive property. It does not depend on how much of something you have. So this amount of gold, or whatever this is, I just totally gave it away, is going to have the same density as a little tiny piece or an even bigger piece. Even though the mass and the volume are extensive and depend on how much of something you have, they combine to form an intensive property. So we can use this density of 19 grams per cubic centimeter to try to identify what this material is. So, for instance, your book gives you a table, it's table 1.4 in your book, that gives you some different compounds and their densities. And if we look at it, we see that gold on here has a density of 19.3 grams per cubic centimeter, which is very close to what we're getting here. So we can probably say that this is a gold compound. So now let's talk about how we can define our measurements. A measurement is precise if it yields very similar results when repeated. It's accurate if it yields a result that is close to the true or accepted value. You can be both precise and accurate, you can be one but not the other, or you could be neither. So we're going to talk about what these mean. So here's some different bullseyes, and where an arrow was shot at them. So in A, notice that all 3 shots are really close together, and they're on the bullseye basically. They're pretty close to the center. So this is both accurate, meaning that it's close to the center, what is accepted, and precise. They all landed in the same area. Next to it, we notice that these shots are pretty close to each other, but they're not at the center. So these are precise, but not accurate. So it's repeatable, but not that close to the actual accepted number. And then over on C, these guys are not accurate, nor are they precise. Okay. There also is another one, so excuse my crappy drawing here. Colored in. Okay. You know what? I'm just going to use one of these bullseyes since I use my crappy. Okay, so let's use C here. Call this D. Let's say it's like this. Okay, all of these shots are in the bullseye, so they're accurate, but they're not that close together, so they're not precise. So you can be accurate, but not precise. You can also be precise, but not accurate. So here's some examples of these cough medicine dispensers. Dispenser number 1, all these numbers are pretty close together, okay, but they're supposed to dispense 296 milliliters. So it's precise, but it's not accurate. These are close together, but they're not the actual amount that we want. Dispenser 2, these are a lot more accurate. Notice they're a lot closer to 296, but they're a little more all over the place, so they're not that precise. But dispenser number 3 is the one that we're going to spend our money on to get the right amount. It's both accurate and precise. That's the one that I would certainly trust to give me the right amount of medicine.